In the last few videos, we've been talking about the carbon cycle and climate change and the current changes to the carbon cycle and human effects and other natural effects that are going on and kind of the problem. And now in this video and next week's video, we're going to transition into solutions, which is really fun. In today's video specifically, we are going to be talking about where energy comes from and the pros and cons of clean and renewable energy options. So let's get started. So first things first, where does Earth get its energy? This image is kind of a little bit of a hint. Yes, that is right. Earth gets 99.98% of its energy from the sun, from solar radiation. Of the total amount of solar radiation we receive, about 30% is reflected from Earth's surface. This is why Earth has what we call about a 30% albedo. It's just kind of the degree of solar reflectivity of Earth. And it's important to note that this is not something that's remained constant throughout Earth's history. It has changed drastically depending on ice cover and other things throughout Earth's history, but currently about 30% of the total radiation that reaches Earth is reflected, and 70% of it is absorbed and converted to thermal energy, which is released. Sorry, my image is covering the word here. It's just IR radiation. It's released as infrared radiation. We talked about the ins and outs of this in my previous video over how greenhouse gases and the greenhouse effect work, so I'll link that to the top right if you're interested. But in any case, there are two more sources of energy to Earth's surface, which make up that last about 0.02% of the total energy that Earth's surface receives, and that is one, internal heat from Earth's interior from formation and radioactive decay of isotopes within Earth's interior. This leads to about a 0.025% contribution of energy to Earth's surface, and lastly, a seemingly negligible, but not negligible amount of energy comes from tidal forces, essentially the gravitational pull of the sun and the moon on Earth. This leads to the tides, but ultimately these tidal forces are very weak for Earth. Interestingly, these percentages would essentially be flipped for things like moons of Jupiter and Saturn, which are very small, and they're next to these huge gas giants that have enormous gravity. Essentially, in those cases, they're in the outer solar system, so the amount of solar radiation they receive is very negligible, and they're very cold due to that fact, but most of their heat comes from tidal forces, the tidal stretching due to the gravitational pull of the huge planets that they're next to. So this particular layout of energy inputs to Earth's surface and their relative percentages is very unique to Earth. This is not the case throughout the solar system, but it is the case for Earth, at least in modern scenarios. Obviously, the internal heat would have been a lot more on early Earth when it was just forming and so on. But today, this is about the breakdown. So if these are the three sources of energy to Earth, which of these sources provides life on Earth energy? Life has to get energy from somewhere, so which of these sources provides life energy? Well, we animals get our energy from eating plants, or animals that eat plants. And plants obviously get their energy from photosynthesis. The reason that's called photosynthesis is because it involves light, sunlight, that's converted to chemical energy. So in other words, photosynthesis, which is driven by the sun, means that pretty much all life on Earth is driven by the sun. I will talk about a slight caveat later in the video in which not all life is driven by photo or light energy from the sun. There are some organisms that are driven by chemical energy, which is kind of different, but we'll get into that. In any case, most life on Earth is driven by the sun. So what about fossil fuels? How do fossil fuels provide us energy? Where did that energy originally come from out of the three main sources that we've listed here? Again, it's ultimately the sun. This is because fossil fuels are preserved organic carbon deposits from ancient life, ancient plants, ancient algae, ancient microbes mostly, and we burned them by converting organic carbon to CO2 very much in the same way that we gain energy from eating and burning organic carbon to produce CO2 through our own metabolisms when we eat food. So ultimately, the energy that we make to live by eating, as well as the energy that we purposefully go and make as humans through fossil fuels, through burning fossil fuels, is all from the sun originally. What about renewable energy sources like solar, wind, hydro, and biofuel? Well, solar is pretty clearly from the sun, hence the term solar. Essentially, the way that at least modern solar renewable energy works is sunlight hits the photovoltaic cells in our solar panels, which excites electrons in the material, converting the sunlight into chemical energy. Essentially, the excitation of electrons converts it to chemical energy. This is much the same of how photosynthesis works. When sunlight hits the plant, it essentially excites electrons in one of the compounds in the plant, and that leads to an electron transport chain that transports the electron down, using it as energy to produce more energetic molecules until it can produce ATP, which is a very energetic molecule that it can break to use as energy to do other functions and cellular maintenance and growing and all that stuff. So it's very similar to kind of that concept, just with a different material, but essentially the electrons being excited and that being used as chemical energy is very similar to how life gets energy through photosynthesis. And that's how solar energy works. But what about wind and hydro? Well, wind and hydro utilize the mechanical energy of flowing water and wind. And if you've seen any of my recent biogeochemical cycle or climate-related videos that I've been posting due to this class that I'm teaching, you've seen that ultimately all atmospheric and ocean circulation is driven by solar radiation. The temperature gradient that solar radiation drives across Earth's surface from equator to poles due to the different angles at which sunlight hits the equator versus the poles. This temperature gradient leads to warmer air masses near the equator and cooler ones near the pole, and obviously warm air rises, cool air sinks. And this leads to atmospheric circulation cells that drive atmospheric circulation, which in turn drive ocean circulation, and then temperature gradients and salinity gradients in the ocean also drive a big conveyor belt of ocean circulation that's kind of separate from surface circulation, which is driven by wind. In any case, all that is to say, you can watch those videos for more details on that, but all that is to say, wind and ocean currents are driven by solar radiation. If you look actually at the breakdown now of incoming sunlight to Earth's surface, and that 70% that gets absorbed and converted to thermal energy, of that, about 45% is directly converted to thermal energy or IR radiation and emitted from the surface. And about 23% of that is stored in water vapor. So that goes into, charging the water cycle, evaporation, precipitation, all of those things. And 1% of it goes into driving wind and ocean currents. And only about 0.08% of it goes into photosynthesis and plants and animals and driving life and fossil fuel production on Earth, and therefore our own energy production. So it's actually a very small amount of the original solar radiation energy that comes to Earth that we actually need or use, which is pretty impressive, just how much solar energy is untouched, by us at least. And then biofuel obviously also originally comes from solar energy, because this is essentially a potential fuel source that involves us using biomass or organic carbon produced by life, plants, algae, and microbes and such, to kind of burn it and convert it to CO2, similarly to how we do with fossil fuels, but in this case using biomass instead of carbon-containing rock, and in that way producing energy. And so, of course, in that case, again, the original energy produced by those organisms to make that biomass came from solar radiation, came from sunlight and photosynthesis. But one question that comes up regarding biofuel is, why is it considered cleaner and or more renewable than fossil fuels if it also involves the burning of organic carbon and converting it to CO2? It also obviously emits carbon dioxide. So why is it cleaner? Well, the important thing to remember is what we're getting the carbon from when we're releasing it to the atmosphere. It's not just the releasing of carbon to the atmosphere that is important to consider, but also where it's coming from. In the case of fossil fuels, we're taking carbon from the geosphere, from rocks, and putting it into the atmosphere. Whereas in the case of biofuels, we're taking the carbon from the biosphere, biomass, rather than carbon that's already been converted into rocks. This is really important because we can renew the biosphere, we can plant more trees a lot faster than we can renew the geosphere, or than we can form rocks. Rocks take way longer to form, and therefore we can't renew fossil fuels by the snap of a finger, but we can plant trees and we can plant more plants. And so using biofuel is way more renewable than using fossil fuels. And we can plant or replant the biomass that we used in this biofuel process at a rate that essentially makes those processes carbon emission neutral. We can sequester just as much carbon as we release through the biosphere, and that is great, but we can't do so when it comes to fossil fuels because we just can't form rocks that quickly. So what about wind energy? What are some pros and cons of getting our energy from wind? Well, it's renewable and sustainable. We won't run out because, again, it comes initially from solar energy, and we're not gonna, wind isn't gonna stop as long as the sun keeps shining and we still have an atmosphere. It also involves essentially no carbon emissions or pollution, of course, after installation. Obviously, when they're still being built and made before everything's set up, it involves transportation stuff, which can involve some carbon emissions. But obviously, the actual mechanism of the wind energy, driving the turbines and getting energy that way, involves very little carbon emission and pollution compared to fossil fuel burning. It also involves very low operational costs once installed. We'll talk about the cons of the setup costs, the initial cost, but operationally and maintenance-wise, it's very low cost. And it can be used in an effective land use kind of way. In other words, it can be put on agricultural land, which allows for dual-purpose land use and kind of helps us, in terms of the space we're taking up. But some cons include the intermittency and variability and just the dependence on weather that day, of the wind energy. And this is kind of a two-factor con in that the wind energy obviously isn't constant. It's not constantly windy, and so it's not constantly producing electricity, and therefore you can have some down period. And the second factor of this con is that there's still a big challenge in terms of storing energy. And so during really windy times where it's overproducing, we can't necessarily store that for a later time that easily or that cost effectively. So that's another con, and that's, a con in a lot of these, a recurring con, as we'll see. But it's also visually not the most aesthetic for some, regions and communities, and also has noise involved. So there's other cons. Also, land use and wildlife impact. Some of the regions where we might want to install wind turbines could have significant wildlife impacts and impact migration patterns of birds and other, habitat destruction. So it's not the best in terms of land use and wildlife impact. And again, initial costs. Obviously, once operating, once installed, operational costs are very low, but initial setup costs can be very high. That's a recurring theme that you'll see in the next few slides regarding the other renewable energies as well. It also has a potential impact on radar systems. So what about solar energy? Well, solar energy has a lot of the same pros as wind energy. It's renewable and sustainable. We won't run out of solar energy, as we've just shown. We use a very, 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 very tiny amount of solar energy as it is. And so we really don't need that much of it. And it's still overabundant in terms of what our needs are, which is great. It also involves essentially no carbon emissions or pollution and very low operating costs once installed. It also allows grid independence. It allows companies that have installed solar panels to be independent of a central power grid and produce their own electricity, and also allows power to be provided to very remote regions that don't have access to such grids. It also shares some of the cons with wind energy. For example, its intermittency and variability. Obviously, during cloudier days or times where the sun isn't shining as much, it's going to produce a lot less energy. And again, energy storage is a challenge. So during periods of over energy production, when there's really, lots of sun capture and energy production, we can't necessarily store that efficiently at the moment or cost effectively. Also, it involves some high initial costs and land use and wildlife impacts, same as wind energy. And in terms of manufacturing and disposal of solar cells themselves, they require materials that present some environmental challenges. So what about hydropower? What about getting energy from the flow of water? So I've separated this one out into a full slide of pros and a full slide of cons because there was a longer list. In terms of pros, hydropower has a lot of the same pros as wind and solar, renewable and sustainable. We won't run out. Very low carbon emissions or pollution. I'll talk about why I said low and not no on the next slide in terms of cons because there are some potential carbon emissions involved. Also very low operational cost once installed. Also, hydropower involves baseload power. In other words, it can generate a consistent, reliable amount of electricity, unlike wind and solar, which, again, we talked about are very intermittent and variable, which presents challenges. And hydropower can be multi-purposed, or the infrastructure involved with hydropower can be multi-purposed for flood control, dams and such, water supply, irrigation. So we can multi-purpose hydropower infrastructure. And energy storage can be achieved. So some facilities can store energy by pumping the water to higher elevations and releasing it back during peak demand. So hydropower has some great pros, but also has some cons. For example, initial costs and time for building the infrastructure required for hydropower is plentiful, and it also has environmental impact. Dams and reservoirs alter water flow, sedimentation patterns, habitats, and ecosystems, and can really harm aquatic ecosystems in the region that it is. It also is limited in terms of where it can be applied. And in some cases, decomposition in reservoirs can produce methane. And obviously that is more carbon emission, more greenhouse emission, and not great for climate change. And lastly, dams and infrastructure for hydropower are vulnerable to extreme weather, earthquakes, etc. So what about energy sources independent of solar radiation? Sorry, my cat literally was making tons of noise, so now she's just sitting in my lap so that she doesn't bother the rest of the video. So anyway, there are some energy sources, or two main energy sources or energy options out there for us that are independent of the sun. One is geothermal energy, which exploits internal heat and radioactive decay, like we talked about earlier with the heat from Earth's interior, or the energy that Earth gets from its internal heat. Geothermal essentially uses this energy. So it seems like a very small amount of potential energy there, but again, based on how much humans need, it's really not that out of the realm of possibility. There's still, enough there for us to use, but there are some, caveats. One good thing is obviously no carbon emissions, but a couple limiting factors include location and potential earthquakes. So location matters for this mechanism because, sorry, my cat is so needy. She keeps jumping down to lick plastic. This is a complete tangent, but she loves to lick plastic. It's a condition. I don't know. She likes the texture. She doesn't eat it. Don't worry. She's not going to choke and die. But anyway, she is making a lot of noise with the plastic bag that's on the ground right now. So I keep having to pick her up and come back to the video. But anyway, so essentially, geothermal energy cannot be exploited everywhere, but in the places that it works pretty well. But it could also cause earthquakes because it involves pumping water down into earth. And we know, we've done this before when it comes to fracking, that can lubricate old faults that are present in Earth's interior, and that can cause them to slip sooner than they would, and that can lead to earthquakes. There are many other pros and cons regarding geothermal that I just don't have time to mention because I really kind of wanted to focus on the sun and its energy potential in this video, so I won't get into it that deeply. And in terms of nuclear energy is great because it has no carbon emissions, but global spread of nuclear tech could be dangerous, if things get in the wrong hands. But there are, again, a lot of pros and cons that I'm not getting into regarding nuclear. I think it gets a bad rep that it shouldn't really get. I think there's a lot more potential with nuclear that is... Maybe I'll make a whole video on it in the future. But anyway, I think it is net positive compared to a lot of people's perceptions of nuclear. But in any case, the last thing I want to touch on is chemical energy. I'm very sorry if you can hear my cat licking plastic right now. Hope, hey. Anyway, I'm hoping the mic doesn't pick it up. But anyway, chemical energy is the last type of potential energy I want to talk about. So essentially, life on Earth gains energy from either producing it or eating it. This leads to two major types of organisms on Earth. Autotrophs, those that produce energy, like photosynthesizers, which take sunlight and produce, organic carbon using inorganic sources, and heterotrophs, which then just get their energy from eating the autotrophs or things that eat the autotrophs. And so they eat the organic carbon. We are heterotrophs. We just eat the organic carbon that the plants produce. But the plants don't need to eat organic carbon. They're making it through sunlight and CO2. So this is the difference between autotrophs and heterotrophs, but there are two types of autotrophs. Photosynthesizing organisms are just one type. They use sunlight, solar radiation, to produce energy, to produce food. But there are also autotrophs that use chemosynthesis instead of photosynthesis. This is the use of chemicals to produce energy rather than the sun. Essentially, chemotrophs, which, are microbes and stuff that can live near hydrothermal vents and such, and they gain energy by using inorganic compounds like molecular hydrogen, hydrogen sulfide, methane, ammonia, carbon dioxide, and other things like that. Other inorganic chemicals sourced from these either hydrothermal fluids or whatever it might be in the oceans. And so there is some talk about how we could use compounds like this, in particular hydrogen, to produce clean renewable energy without the need for solar radiation. Hydrogen is one that is talked about a lot because it burns very cleanly, producing only water vapor as its byproduct, so no other pollutants other than water, which is pretty fantastic when we think about it. But all natural hydrogen on Earth is currently tied up in water or other molecules because, early on Earth's history when it was forming, obviously it reacted with a bunch of things, and any hydrogen that was left over as just hydrogen was like super light and just escaped to space. So there is really no natural, just isolated molecular hydrogen on Earth that we can find and take and use. So what we have to do actually is produce the hydrogen to then use it for energy production. The way we currently do this is through electrolysis. Essentially, we split the water, and the way that we do this utilizes electricity. So this is kind of the problem. The production of the hydrogen is the part of the process that utilizes energy from other energy sources, and then we can make energy using that hydrogen. It's very clean and renewable at that point, but that particular step requires some other type of energy, which is not ideal. So there's a lot of people working on researching this and trying to figure out other ways that we can produce hydrogen and other potential chemical energy sources that have clean byproducts and can be renewable. So a couple key points I want to highlight before I finish out the video. One, fossil fuels and solar, wind, hydro, and biofuel, all of these things get their energy initially from sun. All of these energy sources are originally solar in nature. Sunlight provides so much energy to Earth, way more than we would ever need. So if we can figure out how to directly harness that and store that energy a little bit better, rather than relying on the indirect usage and burning of fossil fuels, that would be really great and more climate friendly. And I also want to emphasize that even if burning fossil fuels had no effect on climate whatsoever, and we could do it and not worry about causing climate change, it is not our way forward. We have to change. We have to switch to renewable energies because fossil fuels, unlike solar radiation, are finite. They are not infinite. We will run out. Actually, there's a debate, at least from what I understand, a certain camp of scientists think that the climate crisis will get too bad to the point that we cannot use up all the fossil fuels. We will not run into the crisis of running out of fossil fuels because climate will become so bad if we did do that. But there's also another group that thinks that we could essentially run out of fossil fuels in a relatively short time frame too, which is kind of terrifying. So even if climate change wasn't an issue, yes, we still need to find another alternative or multiple alternatives to use to produce energy because we cannot rely on fossil fuels forever. And the second key point I want to make is that even though switching to renewable energies and clean energies like solar, wind, hydro, biofuel, geothermal, nuclear, and chemical energies, if we can harness them, is more climate friendly moving forward than burning fossil fuels, this will only solve half our problem. We still need to handle the carbon that we've already released to the atmosphere because this carbon, this legacy load of carbon that we've already released to the atmosphere will continue to warm Earth for years to come, and we need to handle that as well. And that is what I'll be talking about in next week's video over other climate solutions, namely carbon sequestration, or the taking of carbon from the atmosphere through which we can store it in other, chemical reservoirs, other ways that will help combat climate change. So I hope you guys come back for that video next week. If it's out by now, I'll link it up here. If it's members only right now, don't worry, it'll be out publicly in less than a week. So you can check that out whenever it's available. And with that, guys, thank you so much for watching. My references are linked down below as always, and I can't wait to see you guys in the next one. Bye.